Okay, so you made it through the first half of the course. We took the midterm, we're heading into Module 7, and you're going to notice a pretty significant shift in at least the concentration of the course. Up till now, we've been essentially been doing chemistry, basic chemistry, general chemistry, with a lot of the math stripped away. We've learned about how chemicals bond, and we've learned about chemical equations and acid-base reactions and all this kind of stuff. Now we're shifting over to geology, and for the rest of the course, we're going to be doing a lot of geology, and then we're going to do a little bit of meteorology at the end. So don't lose focus. I know it seems like these are disparate subjects, but they're not. And that's why I'm actually including this video here. And this is actually the same video that I showed in Module 1. If you watched it, it's Neil deGrasse Tyson, one of my science heroes, talking about the most astounding fact. And in that video, he talks about the fact that the elements, particularly the heavy elements, that not only make up our bodies, which he talks about, but also the ones that make up the earth and the rocks and the minerals that we're going to be talking about. Where did those elements come from? There's no doubt they came from the crucibles of stars. Stars that have long since gone. They exploded and they spewed their enriched guts through the cosmos. And that debris was the building material for future stars and future solar systems, of which our Earth is a part of one of those solar systems. So don't lose that focus of the big picture. And that big picture is what helps to tie these two sections of the course together. I hope you enjoy the next half of the course.
What is the most astounding fact you can share with us about the universe?
The most astounding fact.
The most astounding fact
is the knowledge that the atoms that comprise life on Earth, the atoms that make up the human body, are traceable to the crucibles that cooked light elements into heavy elements in their core under extreme temperatures and pressures. These stars, the high-mass ones among them, when unstable in their later years, they collapsed and then exploded, scattering their enriched guts across the galaxy. Guts made of carbon, nitrogen, oxygen, and all the fundamental ingredients of life itself. These ingredients become part of gas clouds that condense, collapse, form the next generation of solar systems, stars with orbiting planets. And those planets now have the ingredients for life itself. So that when I look up at the night sky, and I know that, yes, we are part of this universe, we are in this universe, but perhaps more important than both of those facts is that the universe is in us.
Okay, so the book jumps right into it in section 25.1. It's entitled Our Rocky Planet. And if you take my astronomy class, you'll get to learn why the Earth is rocky compared to, let's say, some of the outer planets, which are more gaseous or liquid. But that aside, we won't get into too much in the way of the solar system formation, but just realize that the Earth indeed is made up of really just a handful of elements. They tend to be silicates and metals. In fact, the Earth is mostly iron. And the book describes how the Earth formed about 4.5 billion years ago. It was in a molten state. It was liquid. It was hot. But as it cooled, we had what's called differentiation. That meant the dense stuff in this liquid started to move toward the center, and the less dense stuff was left out near the edge, out near the outer part of the surface of the Earth. So that process of differentiation resulted in a crust, the outside part, which has a different chemical makeup compared to the Earth as a whole. Notice that iron was a big player in the Earth's mass as a whole, and yet it shows up as 5% of the Earth's crust. So iron, which is a very heavy metal, nickel and such, move toward the center of the Earth and form the core, whereas the crust is made up of some of the lighter elements of the Earth's overall makeup. Okay, so section 25.2 gets into the definition of a mineral. What is a mineral? Well, it's essentially a naturally occurring crystalline solid. One thing that you should know about minerals is they typically are inorganic. That means they're non-living. Okay, so minerals can be classified and identified from each other following certain properties. One, it has to do with the crystal shape. Essentially, solids will form regular and repeating structures or arrangements of atoms, and that's what's called a crystal. So as the atoms attach and arrange themselves, you can get what's called crystalline form, crystal structure. And sometimes you can have two different minerals with the same atoms. So for example, graphite and diamond. Graphite and diamond, it's all carbon, right? These are carbon atoms, but they are arranged differently depending on the environment in which these carbon atoms came together. This allowed for a different structure in the formation of the graphite compared to the formation of the diamond, and therefore you wind up with different minerals despite the fact they have the same essential composition. Some other properties include hardness, color, density. We'll talk about more of these as we go through the chapter. Again, crystal form is one way of telling one mineral from another. Another one is hardness. Essentially, it's resistance to scratching. Some minerals are harder, they resist scratching more than others do. And one way of determining the hardness of a mineral is using the Mohs scale. The Mohs scale is described in table 25.1 on page 589. Okay, so one property that's pretty important is cleavage and fracture. A mineral that, when hit, will cleave. That means that it's got relatively weak bonds between layers. So you can actually have kind of layers that will slice off when you have cleavage. Whereas if you have bonds that are equally strong in all directions, then you can break them, but they're going to break kind of randomly, and that's what's called fracture. So there's a distinction between cleavage and fracture. Color is a mineral property that can be, it's tempting to want to determine the mineral identification via color, but it's actually not one of the better properties. Quite often you can have impurities in a mineral that will change its color, and yet it would still be the same mineral. So not super reliable for mineral identification. Density is just the mass to volume. It's the mass divided by volume, and that can be a fairly good distinguishing characteristic of a mineral. So now that you've got the basic feel for some of the properties of minerals, go ahead and take a swing at the skills test entitled Identifying Minerals. And you're going to have to get some practice telling the difference between minerals according to physical properties. While you're at it, put your skills to the test with the lab activity. It's very similar to the skills test. It's just a little more involved. You actually have to positively identify a couple of different samples according to the properties that you're given. So you'll have to kind of match up the minerals that are, the properties that are discovered in the lab with some of the known properties of particular minerals, and then just identify the proper mineral with the sample. If you recall from back in section 25.1, the Earth's crust is 46.6% oxygen, 27.7% silicon. So the 3/4 of the Earth's crust is made up of those two elements. And it turns out that silicon does not exist by itself in nature. It likes to bond. In fact, it likes to bond with oxygen a whole heck of a lot in a molecule called SiO2. That's a silicate or silica molecule. And because of the abundance of silicon and oxygen, it's pretty clear that you're going to have a lot of silicates. In fact, 90% of the Earth's crust is made up of silicates. So that's one easy way of classifying minerals, is to either say, do they have silicon and oxygen? If they do, they're silicates. If they don't, they're called non-silicates. And of course, silicon and oxygen can bond with other stuff, forming various silicates. Some of them contain iron and magnesium. Those are called the ferromagnetic silicates. And you also have the non-ferromagnetic silicates. And they have different properties because of those different elements that are in the structure. All silicate minerals have this same basic building block, the silicate tetrahedron. Now the non-silicates include carbonates and oxides and even native elements like gold, platinum, and iron. The next sections, 25.5 and 25.6, make the distinction between minerals and rocks, and they make clear the fact that rocks are essentially built out of minerals. Minerals are the basic building blocks of rocks. And minerals form from essentially two sources, either magma, which is essentially molten liquid rock, or from solutions. And the type of material that is molten will determine what kind of mineral is eventually formed. So minerals, as it says, crystallize systematically based on their melting points. So materials or elements or molecules that have high melting points are going to be, as a bunch of molten rock or magma cools, the stuff that has the high melting points will also solidify first. As that cools down and gets below the melting point, as the temperature drops below the melting point of a particular element, it will solidify first. So the first minerals to crystallize are those with high melting points and relatively low amounts of silica. The ones that are the last to form, again, the magma is going to have to cool down quite a bit in order to get to the temperature cool enough that other elements are going to solidify or crystallize. Another way of forming minerals is out of water solutions. And this should sound familiar way back when we were talking about the chemistry stuff. When we talked about solutions. Solutions can be described as being saturated, meaning that you have so much solute in the solvent that the solute can no longer dissolve and will precipitate out. So that's one way of creating minerals out of a solution, is with precipitation. When I got new countertops for my house a couple of years ago, I got a chance to go to NF Granite in Olive Branch, Mississippi to pick out my slabs, and while I was there, they clued me into the secret of getting consistent color in your countertops.
There's a specific one, like it's this, let's see, 1, 2, 3, 4, 5, 6, 7, 8 slabs.
Right.
It's considered like a bundle.
Okay.
So it's cut from the same mountain.
Okay.
So that's how we know that it, all the slabs over here looks the same.
Right. I was told that most of the rock comes from Brazil, and primarily the company sells granite, though they do also sell some marble and some quartz countertops. Now, they took me into the shop and gave me a chance to see some of the machines that cut out the rough pieces for countertops, and then I was taken a little bit further back where they showed me where the polishing occurs.
So they do everything, like the cutout for the undermounting, everything is done over here.
Once the pieces have been rough cut by the computers, they move on to the polishing department where they get individual treatment. For example, this particular piece is a backsplash and the worker is polishing off the edges and all the corners. This is a slightly larger piece of a countertop. For the most intricate cuts, a computer is necessary. A template for, in this case, a sink drop-in is fed into the computer, and then the computer runs a robot that cuts the stone. So the next time you see a beautiful countertop, I hope you appreciate the forces of nature that made the rock to begin with, and the mechanical and human hands that made it so beautiful. Just don't take it for granted. Okay, so if you took the virtual field trip to the countertop place, you saw a couple of rocks there, right? Granite. The countertops that they sell are mostly granite. They also sell some marble. countertops, and even some quartz. But quartz, be aware, is a mineral. It's not a rock, because a rock is an aggregate of minerals. It's a collection of minerals. It's a physical mixture of minerals. And igneous granite is an igneous form of rock, meaning that it came from magma that has cooled and crystallized. So igneous, granite rock countertops are essentially an igneous classification of rock. The other type of rock that you saw there, or countertop, was marble. Marble, it turns out, is metamorphic, which means that it came from another form of rock. In fact, it came from limestone, which is itself sedimentary. But that sedimentary rock, limestone, is exposed to great temperatures and pressures and changes its crystal arrangement and forms a metamorphic version known as marble. So become familiar with these three types of rock groups: igneous rocks, sedimentary rocks, metamorphic rocks, because you'll be dealing with these for the rest of the chapter as we talk about the rock cycle. The idea that a type of rock can change into a different type of rock given the proper conditions. I'm going to go through the material here in the next two sections, 25.7, 25.8, fairly quickly as they delve into the details of how igneous rocks and sedimentary rocks form. One thing you should know is that igneous rocks, of course, are formed from lava or magma. Magma, of course, is molten rock underground. Lava is molten rock when it comes above the ground or above surface. And depending on where the magma or lava, if magma solidifies and forms rock, we call that plutonic type of igneous rock. Whereas if the rock forms from lava, we call that volcanic rock. And in your book, they talk about batholiths. Granite is the most common plutonic rock, which means, again, it forms from magma under the ground. Now, as igneous rocks get weathered, they can actually become sedimentary rocks. Again, weathering is just a process either by wind or by water or by ice and freezing and thawing. Rocks can break down, and then the parts and pieces can become cemented together, somehow adhered together to form sedimentary rocks. So there's two different types of weathering. There's mechanical weathering, which is essentially just the physical process of wind or water running over a rock and wearing it down over time. The tidal actions, the ocean just smashing waves on a seashore will break rocks down over time. And chemical weathering can also occur, and that's when you actually have chemical reactions that occur and break down rocks. Now, once the rocks are broken down, they can then start to become deposited, quite often at the bottom of a riverbed or at the bottom of an ocean. You have deposition, and over time, when there's enough sediments that have collected and enough weight, they can start to adhere to each other and through compaction and cementation form sedimentary rocks. Sedimentary rocks can be grouped into two different types: clastic and chemical. Clastic are sedimentary rocks that are made up of individual particles or small pieces of other rock or other kind of organic matter or debris or even organic matter can form clastic sedimentary rocks. And you can kind of tell them apart depending upon the size of the particles. So if it's really, really fine, such as silt or clay, particles that have been smushed together, that might form a shale. Whereas the sandstone, that's made up of slightly larger particles. You can actually see the individual grains of sand that have become adhered together. And then you can even have conglomerates, which are large things. Quite often a conglomerate is made up of large gravels and such, typically particles that are greater than a couple of millimeters in diameter. The other type of sedimentary rock is chemical sedimentary rock, which is essentially We talked about in a saturated solution that you can have precipitates. Well, it's a chemical sedimentary rock is a type of rock that is formed from the precipitation of a particular solute out of a solution. The box on page 605 is pretty interesting because you get a chance to learn about coal and how coal actually is formed. It's formed from organic matter, dead plants that have over time been buried, compressed, heated, and forming essentially coal. And that's why there's such concern about global warming, because what we have done over the last century and a half is we have liberated a lot of carbon. Think about what happens when a plant, what a plant does. A plant undergoes photosynthesis, right? Photosynthesis is just when the plant takes water and carbon dioxide, and in the presence of sunlight, chlorophyll, it produces cellulose, essentially. So it takes all this carbon dioxide out of the atmosphere and makes its own structure. Its leaves, its trunk, all that stuff, its bark is made out of cellulose, this simple sugar. And because it's now part of the tree's structure, it's no longer in the atmosphere. It's essentially been able to sequester, take all this carbon dioxide out of the atmosphere and boom, put it into the tree. Then the tree dies and it gets buried. And again, all that carbon dioxide has been taken out of the atmosphere and it's been locked away. And it's locked away for millions and millions and millions and millions of years. But then humans come along and discover how cool fossil fuels are, and they start burning this stuff. And as they burn it, that's combustion. You learned about combustion. What does combustion do? It releases energy, and it also releases as a byproduct, it releases CO2. So in the span of a century and a half, we have liberated carbon dioxide that has been locked away for millions and millions and millions and millions of years. And that's why the carbon dioxide levels in the atmosphere have spiked in the recent century and a half since the Industrial Revolution. We've also seen a correlation with the global temperatures climbing as well. Okay, during the section on sedimentary rocks, hopefully you appreciated the fact that a sedimentary rock just comes from sediment. And that sediment can be the result of weathering of any type of rock. It could be an igneous rock that gets weathered. It could be a sedimentary rock that gets weathered. It could be a metamorphic rock that gets weathered. It doesn't matter as long as you produce sediment, and that sediment then forms the next generation of sedimentary rocks. In a similar way, metamorphic rocks can come from either igneous rocks, sedimentary rocks, or other metamorphic rocks that are exposed to temperature and pressure, in which case there's a recrystallization, or the rock becomes deformed in such a way that it becomes metamorphized. Now, metamorphosis can occur a couple of different ways, either via contact, such as if you have a pool of magma that moves into an existing rock layer. The rock that's close to that magma is going to get really hot, and it's going to start to become metamorphosed. This bordering, especially this area, the closer you are to the new heat, the more these rocks are going to change, and it's going to decrease the farther away you get. That's contact metamorphism. Regional metamorphism is when you have a change in rocks over a much larger area because of a much larger change, such as like a mountain, two tectonic plates smashing into each other and creating a mountain will actually create a lot of temperature and pressure over a large region, which will create metamorphosis of the rocks over a much larger area. The metamorphic rock can actually have essentially two classifications: foliated, which means you can actually still see the layers, or non-foliated. And as I've sort of hinted at, just like sedimentary rocks can come from any type of rock, metamorphic rock can come from any kind of rock. Notice that there's a lot of cycling that goes on. So you have magma, which then cools and forms igneous rock. That igneous rock then can be weathered and form sedimentary rock. That sedimentary rock can then be kind of smushed together, compacted, and exposed to heat and pressure turned into metamorphic rock. That metamorphic rock can then be melted back into magma and so forth, and the cycle continues. But notice that it doesn't have to be just a circle. There are actually some ways of cutting through. So igneous rock can be changed via heat and pressure to metamorphic rock directly. Metamorphic rock can be weathered and created and resulting in sediment. Sedimentary rock can be deposited, weathered, and deposited as sediment as well. So there's little cut-throughs in this rock cycle, but the rock cycle is going to be very useful. Understanding the rock cycle is useful in the activity that you'll be doing called the skills test, the rock cycle. So make sure you understand that basic diagram there, and that'll help you complete this skills test activity. And finally, if you've been playing along at home, these are the answers to Chapter 25's Readiness Assurance Test at the end of the Chapter 25 review materials.